I'm Dario Amodei, and I'll be talking about language models or few-shot learners, also known as GPT-3. I first wanted to acknowledge the large number of people who contributed to this paper, as shown on this slide. GPT-3 is a 175 billion parameter unidirectional transformer language model. It's a pretty simple architecture. At its heart, it's basically a scaled-up version of its predecessor, GPT-2. The thing that motivated us to scale up GPT-2 into GPT-3 was the observation that the loss of a language model decreases predictably and monotonically as the size of the model increases, which motivated us to want to train a very large model to see how low its loss could be. This is shown in the yellow curve, and we see that it's exactly on trend. The main scientific contribution of GPT-3 isn't the model itself, but an emergent property of the model that emerges when you scale it up enough. Few-shot learning. Few-shot learning has been seen before for smaller models, but it's a much stronger effect for these large models. The basic idea behind few-shot learning is you train your model on a large number of documents. They contain various patterns that the model has to learn to infer. And then at test time, if you give the model several examples of a task, that's another pattern that it can either match to something that it's roughly seen in the training data or learn from scratch. It's roughly analogous to some kind of meta-learning. So we ran GPT-3 on a large number of NLP tasks and observed two things. First, as expected, the performance of the model improves monotonically with model size on all of these downstream tasks, not just the loss. But second, and more importantly, the gap between zero-shot learning and few-shot learning, which represents how much adaptation or pattern matching the model is able to do, that gap itself grows with model size, which shows that few-shot learning is getting better. We do a lot of evaluations in the paper, and there isn't time to go through all of them here, but as a kind of heuristic overview of how the model does, there are some tasks like closed tasks, completion tasks, language modeling, closed book question answering, where the model performance is very strong and sometimes even outperforms the fine-tuning soda. There are other tasks like translation and Winograd-inspired tasks where the model does well, but doesn't quite reach the fine-tuning soda. Then there are tasks like common sense reasoning, reading comprehension, and superglue that are uneven. Some of the tasks the model does really well at, some seemingly similar tasks it does poorly at. Finally, on natural language inference, the model does very poorly, basically no better than random chance, and the model also has significant bias issues, which we are continuously working to try to fix.